All right, hello there, guys. My name is Oliver. I'm in Calc 1 spring semester in Professor Crackmo's class, and I'm here to tell you there's been a murder. Now, we know a couple facts about this murder. We know that the weather was exactly 20 degrees Celsius when the murder took place. We know that the body temperature at 1:30 when we first found the body was 32.5 degrees Celsius, and the body temperature now, 1 hour later, is 30.3 degrees Celsius. Now you're probably wondering, what can we do with all this information? We can use Newton's cooling law to tell us exactly when this man was murdered. Now Newton's cooling law states that the derivative of temperature over the derivative of time is equal to k, some constant, times the temperature minus the temperature of the surroundings. Now you first look at that and you know what, you can't really do much with it, but we can manipulate this to help us. So we can go ahead first and call this right here, we can call this y. So we could rewrite the equation, and instead of using the derivative of temperature, we can now call temperature y, because we have thus substituted the temperatures out of the equation for y. So now we're left with the derivative of y over the derivative of time is equal to k, some constant, times y, which is just t minus ts. Now there's two different ways we can go about manipulating this equation here to bring us to the equation where we need to solve the problem. First, we can see that we have a kind of precarious situation here. We have the derivative of something, or the derivative of y over the derivative of time is equal to k times that very something. So the only thing that is going to give us a constant in front and then that something is going to be this equation here. Alright, so now our next step is to take the things we know and try to make heads or tails of them. So we can see the weather, and we're gonna go ahead and call it the TS, which is the temperature of our surroundings, which you already have outlined over here. We have the body temperature at 1:30 p.m., which was 32.5 Celsius, and we're gonna call that the temperature at 0. And this is gonna be time, 0 here. And then here we have the body temperature an hour later, and that's 30.3 degrees Celsius, and we're gonna call that the temperature at 1. So now we know quite a bit. So what we can do is we can try to actually solve for y sub o right here. So what we're going to do is we're going to solve for y sub o. And the first thing we're going to do is take a look at our equation here and figure it out. So we'll take this y sub o, and we're going to go t at 0, which is 32.5, minus the temperature of the surroundings, which is 20 degrees. And that's going to simplify and give us 12.5. So now that's going to be our y sub o. And we can go ahead and plug that directly into here, because this is also going to be y sub o. So we can go ahead and plug that in, and we know that y sub o is equal to 12.5 e to the k, and we know that up here this temperature is going to be at 0. So that's going to actually give us itself. So lo and behold, y sub o equals 12.5. So anyway, I think we're pretty clear with up here, so I'm just going to give it a quick erase. That was the longest erase in the history of mankind. But anyway, now that we have y sub o and we know what that is, let's try to solve y of 1. So how that's going to work is we're going to go y of 1 is equal to y sub o, because that's a constant, or that's one of the constants in the equation. You always have to use y sub o, which is 12.5, E to the K, and then now we've dictated the temperature at 1 to be this, 30.3 degrees Celsius. So, booyah, we've got something going here. All right, so actually let me correct myself. This is actually K to the T as in time. So our time is going to be 1. And over here I misannotated it as time as well, so please forgive me. I'm just going to go ahead and correct it really quick. So now that we have this, we can go ahead and plug in this 1 into there. So boom, this can be 1. All right, so now that the corrections have been made, we end up with this. And the thing is, we know what y sub 1 is, or we can figure it out. Because over here, we did t sub 0, but we're going to go ahead and do t sub 1. And we know we actually have a t of 1 right here. So that's going to be 30.3. So this new equation over here is going to be 30.3 minus 20. And that's going to give us 10.3. So we can go ahead and now rewrite this equation as 10.3 equals 12.5 e to the k. And then now we have this fancy awesome thing called logarithms that we can use. So we're going to go ahead and do the natural log of both sides. All right, I made these fancy things called logarithms, which I will use in just a moment, but I realized we can simplify by dividing. So I'm going to go ahead and just divide both sides by 12.5. And that will then eliminate this to give you 10.3 over 2.5 equals e to the k. Now we need to isolate that k so we can use the beautiful thing that are logarithms. So let's go ahead and times both sides with the natural log. And then now this undoes this, so we're going to end up finally with the natural log of 10.3 over 12.5, and this is the natural log of all of that, equals k. So now there you have it, we've solved for k. So this is huge, and then now all we have to do is to find the time that we need is to just plug in this k and plug and chug. So let's get started. All right, so now we're almost there. So what we're going to do is now we're going to solve for the y of time killed, which is actually t of time killed, which we're going to use up here. Bam. So we're going to plug in those numbers. So we're going to get TO, which is actually going to be his initial body temperature, which is 37 degrees Celsius, or 98.6 for us Americans. So it's going to give us 37 degrees minus the surroundings. So it's going to give us 17. So now we have the y of the time killed. We're going to plug that and the constant into the equation to solve. So here we go. We're going to get 17 equals 12.5 e to the negative point, hold on, what was it? 0.193584741 numbers. And then up here, time killed, which is what we're really after, is this little gem over here. So we're going to go ahead and divide. All right, we're actually running out of room, so let me erase some stuff and keep. All right, so we're back. I went ahead and just rewrote the division up here. So we're going to divide 17 by 12.5 that we did down here, and that's going to give us 1.36 equals e raised to the negative k. And I'm just going to define k up here because it's such a long, wordy number that we're just going to define it and move on, and I'll keep using k until we need to calculate. 0.193584741. So now we take the natural log of both sides, and that undoes that logarithm. So we got ln 1.36, or the exponential, sorry. Ln of 1.36 equals negative k, which is this number over here. Time killed. So now what we need to do is divide by k. So we'll just divide by k. Or negative k. And then that'll give us our time killed. So if we do the calculations, so after punching in the TIE4, love this thing, my favorite. We end up getting the time killed equaling negative 1.58837. We'll round it there. So we end up getting negative 1.58837. And now this is 1.58 hours, because our times are in hours, before this time at 1:30 that we initially calculated. So that gives us 11:54:43. Now that, my friends, is how you use a little Newtonian physics, little elbow grease, some smarts to solve a murder. Now that is something to drink to. One less murder in the world. Thank you very much. Hope you enjoyed.